This open bag of chips doesn't have a way to reseal it. It represents a dataset with a missing feature. Sometimes you can fill in missing pieces in a dataset with another dataset, but in this case, I can't fix the broken seal with another bag of chips. But I can come up with my own solution for fixing the hole, rolling it up and closing it with tape. If you can't solve your problem in a data-driven way, there are ways to solve it artistically. You may be able to augment your scientific visualization with scientific illustration. Though for anything called a visualization, a good rule of thumb is that at least 80% of your content should be data-driven. Scientific illustration can come in handy if you have a missing gap in your data that can't be filled in with another dataset, or if you want to add context around your data. These spherical objects are microscopic organelles called chromatophores. The chromatophore model is a scientific simulation. In this video, you see many copies of the chromatophore model grouped together into a scientific illustration of purple bacteria. The bacteria shape isn't a simulation, but was created by hand, under careful supervision of the science experts and based on real photographs, but not actually using data to drive the results. This is an example of using scientific illustration to create a context for data visualization. This visualization of the inside of the sun aims to show the rolling convective waves just below the surface. The simulation that shows this only models the outer one-third of the sun's interior. Since we're using an analogy of X-ray vision to look inside the sun, audiences would expect to see a core at the center, and not just an empty shell. We looked for a simulation but couldn't find one because it turns out that the sun's core is quite simple and can be modeled statistically. So we made our own core, basing the density on a published scientific paper. It's generally a good idea when incorporating illustrative elements to guide your illustrations with data wherever possible, because even some data is better than pure imagination. These illustrations help with the narrative of the visualization by showing the viewer things that they would expect to see, because they do exist in the real world, but they aren't part of the simulation. Elements that enhance the audience experience but aren't of research interest to the scientist can be beneficial in a scientific visualization meant for the public. Another non-scientific enhancement is artificially increasing the resolution of a simulation. Let's take a look at an example. Here is a low-resolution volume. We can take a look at a slice through the center of the volume to get a better look at the detail. You can actually see the little squares that make up the voxels of this volume. At this scale, the volume's voxels are much bigger than the screen's pixels, and they look blocky. What we can do to fix this is to sample the low-resolution volume into a higher-resolution volume and interpolate over the additional voxels. This makes the volume appear smoother. Generally, interpolation is a concept where you take some start and end values and use that information to figure out what happens in the middle. Temporal interpolation means interpolating over time. There's yet another type of interpolation, spatial interpolation, that interpolates over an area of space. Let's say this is our data set, where each colored box represents a different data value. We want to increase the resolution of our grid by turning it into a grid that looks like the one on the right. First, we copy over the original data values to their respective positions in the new grid, and then we interpolate the values in between. This only works to an extent. Interpolation isn't going to create any more data points, so you aren't going to see any additional features or more or better data. It's a useful trick for making an existing data set look a little nicer, but if you need a lot more resolution, you may be better off finding a different data set. We're talking about ways to make your visualization look better, but what if it's too perfect? Computer-generated imagery often looks fake and unnatural because objects are perfectly smooth and the image is perfectly clean, but real-life objects are often random and dirty. We expect the disordered randomness of the real world when we see live-action movies. There's atmosphere and haze in the air, lens flare on images shot with a physical camera, pores and wrinkles on people's skin, wear and tear on surfaces. You can add imperfections into your visualization to make it look more realistic, with a bit of algorithmic noise. Noise in general refers to randomness. It can be a bad thing if it's unintentional, but you can use it purposefully as well. You can add noise to a surface in your scene to make it less perfectly smooth by assigning a wave function to its coordinates in 3D space. Or you can add noise to your 2D image to make it look less clean and rendered. This can have a bonus effect of actually looking more like something recorded on a physical camera. Videos that are shot in physical film often have visible noise called film grain, which is an optical effect that happens due to tiny particles of metallic silver or dye in the film itself. Virtual cameras don't have film and therefore don't naturally have this noise. But filmmakers often actually add this back in digitally because audiences are used to seeing it, and it adds to the movie look. Not all noise is the same. There are many different noise algorithms that produce different looking effects. One of the most famous being Perlin noise, which was developed in 1983 specifically for the purpose of making computer-generated surfaces look less machine-like. What all noise does have in common is that it's implemented as a mathematical function that creates a texture of values within some range, often between 0 and 1. The noise function can be one-dimensional and return a single number per position, or three-dimensional, returning different values for red, green, and blue. Noise can be random or regular. You can combine different types of noise to create pretty advanced geometry or effects. The positions and large-scale heights of these mountains on the surface of Venus are data-driven, but the smaller texture and fluctuations on the surface are a result of noise. If you are looking to make a randomized, not data-driven environment, you can actually use noise to make the mountains themselves as well. Layering noise functions can increase the naturalistic look of a texture. You can use combinations of noise functions to create realistic-looking clouds, with different types of clouds like you would expect to see on a real planet. Whether you're making your visualization noisier, higher resolution, or combining it with scientific illustration, making it more aesthetically pleasing to an audience can help with their enjoyment and their understanding of the data and its context. Fun fact: scientific measurement instruments detect a lot of noise, and it can be a challenge to decipher whether something is noise or a feature. In 1964, astronomers detected a signal from a radio telescope that they couldn't explain. They thought it was noise and searched for all possible causes of the noise until they found pigeons living in the antenna. Thinking they solved the problem, they ushered out the pigeons and cleaned the instrument, but the noise persisted. It turns out they discovered the cosmic microwave background, a very faint radiation signal that permeates all space in the entire universe. This radiation is left over from the Big Bang.